Hi, I'm Helena Lenikova, and this will be the Azure Spatial Anchors Linux SDK for robotics research demo. The learning objectives for these demo are, first, to get a closer introduction to Azure Spatial Anchors and how the service works and how it can be used. Second, we'll show you how to use the Azure Spatial Anchors Linux SDK with ROS on either a robot or with the provided data from an Intel RealSense T265, which you can see on the right here. And we'll also show you an example of how to add Azure Spatial Anchors support to the Unity demo in demo 1 and how to adapt it to actually work together with your robot if you happen to have one at home. So here we'll show you a little demo, a little preview of what the demo is going to look like in the end. So here's a real ClearPath Jackal with its virtual position overlaid on top of the real object. This is a scene from a HoloLens. So we're using Azure Spatial Anchors here to co-localize the two devices. You can see where the anchor is located in space here, and both the HoloLens and the robot are using Azure Spatial Anchors to find a common coordinate frame. So first we'll talk a little bit about the Azure Spatial Anchors Linux SDK and exactly how it works. So this is going to go back to the previous lectures where we discussed Azure Spatial Anchors, just as a little refresher. So what is a spatial anchor? We use it to refer to a common reference frame for placing digital content. The main thing is that the anchor is supposed to be stable relative to the real world. So in the case of Azure Spatial Anchors, these anchors are persistent over time and they're stored in the cloud. So you need an internet connection to be able to access them. And of course, you can place digital content on top of them, and in the back end, they're actually stored as collections of sparse visual features. So what exactly is an anchor? How do we access them? How do we use them? How do we refer to them? So in our case, anchors are referred to by an ID, which is a 128-bit UUID. We'll see some examples later. And it contains a 6-degree of freedom pose relative to some visual features which you don't have access to. This is kind of taken care of by the service. All you need to know is the ID. So other important things to note is that the service doesn't store the original images. In fact, they are not even sent to the service. All we're getting is the extracted feature descriptions and triangulated 3D points. So here you can kind of see an example of what the chair from the previous slide looks like. So these black points are just triangulated 3D points, and each of them contains some key point descriptors. So these are visual feature descriptors that encode some information about the neighborhood of the point. And so these are quite descriptive so that you can match them from frame to frame, and you can match them when you revisit a scene. Another cool feature of doing this as a cloud-based service is to actually improve the anchors over time. So if you originally create an anchor and turns out either the scene changes or the lighting changes, or you just didn't get very good viewpoints on it the first time, if you make successful queries against this anchor will actually improve. So you, in the future, will be able to get more accurate localizations to it. And what's also really important to understand is anchors created in Azure Spatial Anchors can only be accessed from the account on which they're created. So if you create an anchor in your bedroom, no one else can localize in your bedroom. Only people with access to the Azure Spatial Anchors account and your bedroom would be able to make use of this. So how does Azure Spatial Anchors work? Again, this is a review from the previous lecture, but just to cover it again. So on mobile phones, we're using the images and the poses from AR systems such as ARCore and ARKit. On the HoloLens, we're using image features and poses from the head tracking stack. So this is the pose estimation SLAM system that's running on board the HoloLens. And on the robot, we're getting undistorted images and poses from the robot's own SLAM or state estimation system. So we'll talk about the requirements of this in a second. And what can you then do with this information? So it's going into the SDK here. And then all of these images are stored together in a session. So a session just means basically within one short span of time, You can think of it as a trajectory, basically. It's a history of the poses you've had and the images and visual features associated with them. So all of the data within a session can be used to create an anchor. So this means anything you kind of observed before clicking Create Anchor. This would then use all of the visual information that's in this session to create an anchor, and the actual pose of the anchor can be freely defined relative to these 3D features. So you don't need to, create anchors on a corner or on an edge. They can be created in free space. They can be created inside objects. It doesn't really matter because the actual coordinate system of the anchor is quite arbitrary. When you create an anchor, you get an anchor ID back. So again, this is this 128-bit UUID. This UUID is unique. And within the same Azure Spatial Anchors account, you can then use it to reference that anchor for queries. So querying is basically trying to find the anchor in what's so far been seen in the session. So this will use, so if you query an anchor, this will use any of the information that's already in the session to try to determine, can I see this anchor in the scene? If you can't, then it'll wait and use more information in the session before letting you know its pose. And when you query an anchor, what you get back is the relative anchor 6 degree of freedom pose. So this pose is relative to whatever coordinate frame your poses are in. So this is going to be the pose of the anchor relative to, for example, your odometry frame, not to your current position. We'll talk about this a little bit more. There's a few things you should know about Azure Spatial Anchors and how we're going to use them. So the first is that Azure Spatial Anchors is a cloud service that requires both an internet connection and a free Azure account. The second is that anchors are linked to the account in which they're created and can only be accessed from that account. So again, your anchors cannot be used by anyone who doesn't have your account credentials. Next up, so when you're creating an anchor, only the information in the session up until the anchor creation request is used. This means if you walk around with your camera and then get lots of data, create an anchor, and then keep walking around with your camera, the information that's that you gather after creating the anchor is not used, it's discarded. And the same goes also for querying anchors. So if you walk around with your camera and find an anchor successfully, and then you gather more information, that information is not used to refine your anchor. You only continue using information up until the point where you actually find the anchor the first time. And this also means that the queries do not get refined. So again, all information after you first successfully find the anchor is discarded. This means if your odometry system drifts significantly after finding an anchor, then you should start a new session from the kind of new odometry frame and query again. But this is quite easy to do in the SDK, which we'll show you in a little bit. And 10,000 queries per month are free with Azure Spatial Anchors. So again, you don't need to pay anything to use this for normal use cases. Next up, we'll talk about how Azure Spatial Anchors works with ROS. So we provide some ROS wrappers, so it's easy to get started with your own robot or SLAM system. So here's a little bit about the system. So you have the ASA ROS Node. This is what's running live. We also have a bag parser in case you want to consume kind of offline recorded data. They both work more or less the same. So for subscriptions, you only subscribe to really two main things: an image topic and a camera info topic that goes along with the images. See, these should be published at the same timestamp. And some source of transform. So this can either be TF or a transform message that gives you the pose of the camera and the transform frame. And we'll go over in detail on the requirements on these in a little bit. There's a few different service calls. So you can create an anchor, you can find an anchor, and you have two different ways to reset a session, which we'll talk about in a little while. And once you actually get data into Azure Spatial Anchors, you need to be able to get it back out. So you first get information on the ID of the anchor you've created. You get information about any found anchors in the space. And then, of course, all of the found anchors are published on the TF tree as the static TF messages. And there's a couple of required parameters for running this. So as we discussed before, you need a Azure Spatial Anchors account, which consists of an account ID, an account key, and an account domain, which tells the service where it's actually homed. Let's talk about the input requirements for data you put into the Azure Spatial Anchors Linux SDK. So you really only put in two things, images and poses. So for the images, they need to already be undistorted. So all camera lens effects need to be removed. We'll talk a little bit about different ways to do this, especially for the Intel RealSense T265. We have a solution that should do this out of the box. The images also only need to be grayscale. It's fine to put in color images, but the data will not be used. You also need to provide the intrinsic calibration of the camera, which includes the focal length, both in X and Y in pixels, and the principal point of the image, X and Y in pixels. Again, you do not need distortion parameters because we assume the images are already undistorted. The way you put this data into the ROS interface is through sensor messages image and sensor messages camera info. These two need to have matching timestamps. So any camera you use in ROS will generally output both of these with correct timestamps. Next up is you also need the poses. So this is supposed to be the full 6 degree of freedom pose of the camera frame. So not of the robot itself, but of the camera frame. And this needs to be timestamped on the same clock as the camera images. So this means, you can't have timestamps months apart. This also means that normally to get better performance, especially in fast-moving scenarios, it makes sense to have both the camera and your pose estimation system be on the same device so that the clocks match. So these poses should be expressed in a constant odometry frame. So this is some kind of world frame that's not moving. And of course, preferably not drifting and preferably not jumping. If you have significant jumps or very significant drift in your odometry frame, you should reset the session, which using one of the reset service calls. And so there's two ways to get your poses into the ROS node. The first is to use just a transform stamp message, which assumes you give us the transform directly from the odometry frame to the camera frame. And the second is to use the TF tree. So here you can, for example, have a base link, then link to the maybe some sensor mount, then link to the actual camera frame, and we'll be able to resolve the full tree to get the correct pose of the camera at the correct timestamp. So here's an example of what kind of data we're expecting. So here's an undistorted image, going through and the corresponding poses of these images over time. So this is the kind of data you need to be able to feed in from your SLAM system. So a little bit about coordinate system conventions, because these vary from framework to framework and are very important to get right. So we assume that our odometry system, so basically this kind of static coordinate system in the world, is Z up. So gravity points in the Z down direction. So this is important, especially for matching across devices, as the gravity direction is used for feature matching. So this is the standard ROS convention. So as long as your robot is following standard ROS conventions, you shouldn't have any issues. If you have a really arbitrary system set up, please convert it to Z up. Much more important is the camera coordinate system. So again, there's a few different conventions for this. The convention we use is Z into the image. So in graphics, it's often the opposite. So make sure you get this right. Again, this is the standard ROS convention that most camera drivers should match. But Z is pointing into the image, X along the X-axis, and Y along the Y-axis of the image, which you can see here on the bottom. And of course, the final thing, the coordinate system of the actual anchor you create can be completely arbitrary. So all that matters is the direction of gravity being correct in the world coordinate system and the direction of the image frame being correct. So to kind of make this easy to use, since of course there's an infinite number of different robots, camera systems, SLAM systems, and so on and so forth, we've set up some examples with the Intel RealSense T265. So this is an off-the-shelf visual inertial SLAM sensor you can just buy for around $200. So it features a stereo fisheye camera. These are both grayscale. They're very fish-eyed, which means they have a very wide field of view, which makes SLAM work better. They also have a hardware time synchronized IMU, which is used for interpolating between image frames. And most importantly, they feature an onboard SLAM system. So this means that basically you plug this into USB, you get images out, and you get the pose of the camera out. So it's super powerful device, and in our experience, it works quite well for a lot of different robot applications. And again, it's only $200, and I'm not receiving any money to advertise it. So next up, we'll go through the demo instructions. So how exactly to set up the Azure Spatial Anchors Linux SDK and the ROS wrappers. We have some sample data sets from the Intel T265 that you can use to try it out in case you don't have a robot or a sensor ready to go. Next up, we'll discuss how to then basically adapt the demos from demo 1 to work with a real robot and allow you to interact with a physical robot using mixed reality, similar as you saw in the preview, and what kind of changes have to be made there. And so at the end of this demo, you should be able to use Azure Spatial Anchors on your own robot to enable human-robot interaction. So before we get started, just to be very clear on the requirements of following this tutorial, so you'll need Ubuntu 18.04, 19.04, 20.04. The tutorial was made with 18.04 in mind, but we'll point out when things are different for 20.04. The changes are very minor. You'll need either ROS Kinetic or Melodic. You'll also need an Azure account to create an Azure Spatial Anchors account. This is free, so there's no need to give your credit card information, and for the first 30 days you'll get $200 free of Azure credits, so you can also try out fun other things on Azure, train some deep learning networks. Next up, you'll also need to have signed the EULA to have access to the Azure Spatial Anchors Linux SDK. So there's a link here which you can click, and it's also in the description. So you need to sign this EULA for us to be able to give you access, as the Azure Spatial Anchors Linux SDK is only for research and not for commercial purposes. So please sign it. It might take up to 1 or 2 business days for us to be able to give you access, as this is a manual process. And in case this changes, we'll write in the description of the tutorial. And so all of the setup instructions, if you don't want to listen to me walk through them, you can also just read all of them at this link, aka.ms/ASA Linux SDK.
To get started, we first need access to the Azure Spatial Anchors Linux SDK. As this is a research SDK only for non-commercial use and offers no support, we ask you to accept a EULA before you can gain access. To sign up, simply go to aka.ms/ASA Linux SDK sign up. Here you'll have the form. You just need to fill in your full name, email address. So please note that you need to have an Azure DevOps account. So you can do a sign up here. It's also free. And you can also use your GitHub account, but you need to give us the email that's associated with your DevOps account in the end. And to help us out and give us some more information about who's actually using this, please fill out what kind of researcher you are and what you plan to use the SDK for, and of course accept the EULA. Again, the most important part is this is for research only and non-commercial use. After filling out the form, it might take us a little bit of time to add you to the project. This is done manually, so please be patient. And in case this workflow changes, we will update the ROS wrapper documentation so that you don't need to do this anymore. So after we give you access, you can go to the repository linked in the email you get. And here you're able to get access to the Debian package that wraps the ASA Linux SDK. So we're currently supporting Ubuntu 18.04 and 20.04, though you should be able to use 16.04 if you also install GCC 7. So once you have access, all you have to do is download the Debian package and simply follow the on-screen prompts to install. In case you're doing this on a robot or something without a UI, you can also, of course, install it from the command line. First, we're going to create an Azure Spatial Anchors account. To do so, go to portal.azure.com. Create a new account if you don't have one yet. This should be free. You can do so on azure.com. So again, here you can try Azure for free and you'll get $200 of free credits for the first 30 days, and there'll be quite a few services you can keep using. So you don't need any money for any of the things we're going to show you here. So back to Portal, you'll want to create a new resource, search for Spatial Anchors. And press Create. You'll have to select your subscription. You can create a new resource group as you do this. Here we'll do so, call this IROS 2020A, and call this IROS 2020A ASA. For location, just select whichever one is closest to you, so you get the least latency, or the default is East US 2. It takes a few seconds to deploy. Then you can go to Resource. So here you have a dashboard with a few things you can look at: anchors created, anchors deleted, anchors updated, queried, and poses found. So these all take a few minutes to update, but you'll be able to check whether you're querying or creating anchors correctly on this panel. The most important things you need to look at now are account ID. So copy this to clipboard and save it somewhere. The account domain, so if you create it on US East 2, it's mixedreality.azure.com. Otherwise, it's going to be West Europe, mixedreality.azure.com, and so on. And the final thing you need to get is the access keys. So these are the developer keys that you can use to access the service. So again, you should write these down. We'll need these in a second to set up the ROS node. So there's 2 active at any given time, and you can refresh either of them at any time. So let's say I accidentally sent someone my primary key that I didn't want to have it, so you can just refresh it like this, and then you have a new primary key and the old one is invalid. Okay, next up we need to install the system dependencies. So this means installing ROS. So if you already have a ROS installation, you can skip a few minutes ahead. So you can simply follow the instructions in the GitHub repository. I'll quickly walk through. It's also, if you Google install ROS Melodic, you should get the same results. But let's do this. Next up, we're going to want to install ROS Melodic Desktop. So this will give you basically a few visualization tools, basics of ROS, but nothing too big. So I think this is a good package size to start up. Okay, now after a couple of coffees, the ROS install is done. So we'll continue following the instructions from the GitHub repo. So I've copied them here just so it's a little simpler to see. So first up, we'll source ROS Melodic into our bash RC. This gives us all of the paths and access to binaries in ROS, and resource our bash RC. We do this step because if you're following 2004, all instances of melodic will have to be replaced with noetic, which you can also just do with ROS distro here. In case you're following some of the instructions and you get invalid packages such as this, then it's because you haven't sourced opt-ROS melodic or noetic setup.bash. So please make sure to do that. So next up, we're going to install some of the system dependencies. So there's a few things here, mostly the Catkin build tools, a few packages, and gflags and glog, which we use in the repository. While that's building, I'll talk through a few of the other things. So here we have a couple more packages that need to be installed. So perception, common messages, and so on. So these are just, again, common ROS packages. And then we'll move on to how to install the repo. You need a little bit of hard drive space for this. Okay, that's now finished. Let's continue. So next up, we will set up our Catkin workspace. So normally this is in your home folder under Catkin workspace. So here we've made the directory, and we'll do some setup steps. So these are really important. And here you can see that the double space layout is merged. This should be set to merged for this system to work. And here we're extending opt-ROS melodic, which means you can use all of the other ROS stuff. And we're going to explicitly extend the workspace. And then add this so that we always have this workspace handy. Next up, we'll actually clone the repos that we need. So Catkin simple, this is just a kind of a helper package to build this, and then Azure Spatial anchors. Okay, now we have the Azure Spatial anchors folder here. And remember, you need to have this Debian package of the Azure Spatial Anchors Linux SDK actually installed. So you should have, hopefully by this point, gotten access to it and can follow the instructions to download the deb file. Simply double click and press install. And now, if all goes well, we should be able to just say Catkin build ASA ROS. Fantastic, that built successfully. So now you can source bash RC or open a new terminal, and you should be able to then have completion for example, ASA ROS.launch. Next up, let's get some data to actually be able to use this. So you can also use a Intel RealSense T265, as I said before, but in case you don't have one or just to get started easily, I've prepared two data sets you can use. So one is small, which is roughly 600 megabytes, and the other is large, which is 3.3 gigabytes. Again, you need a little bit of hard drive space for this. So download one of these data sets. Then once it's downloaded, unzip it to, for example, data IROS 2020. First, let's go over some launch files so we know what the options are for what we can do with this ROS wrapper, and then we'll also talk a little bit about how to create anchors, query them, and some considerations. So let's take a quick look at the launch files. So within your Catkin workspace in the source directory, there should be an Azure Spatial Anchors ROS folder. And within that, in ASA ROS, there's a launch file directory. So there's two options here. So ASA ROS.launch will launch the actual node, and Intel T265.launch contains the launch files to run the drivers and undistort the images in case you happen to have an Intel RealSense T265. Further instructions for this are on the wiki for the repository. Right now, though, we're going to take a look at ASA ROS.launch, which is going to run the actual Azure Spatial Anchors node that you can use with either recorded data or with a live running robot. So let's take a quick look at what kind of options we have here. So first you need to give your credentials for your account. So this is your Azure Spatial Anchors account you should have created. And so what we can quickly do here is just go back to Azure Portal and copy and paste the account ID and the access keys. And if you're watching along, please use your own account. Don't use the one I'm using here. Then, of course, also make sure that your account domain matches the one in the overview. So here it's mixedreality.azure.com. This is if you have it created in East US 2. So next up, we have a couple more options. So first, an anchor ID. So this is the ID of the Azure Spatial Anchor you'll start looking for on startup. So this can be a comma-separated list of anchor IDs, or it can be left blank. In case this is blank, you just won't be we won't be looking for anything on startup, but you can always call a service call to start searching for new anchors. Anchor frame ID, so by default, this is going to be the ID of the anchor, and this refers to the TF frame ID that's output. So in case you want to track a lot of different anchors, you should just leave this blank. If you want to track one specific anchor, as in our upcoming demos, it makes sense to set this to a TF frame name that's unique and distinctive. So in many cases, anchor. Another thing for debugging that's quite useful is the sprint status option that's false by default. So this will let you know basically what the service is saying about the data that you're putting in. Most importantly, if you're creating anchors, it'll let you know once it has enough information about your environment to create the anchor or not. And so here you also see all of the other settings. So for instance, the remapping. So this is really set up to already work with the recorded data that's provided in the bag file. So this is again recorded from a Intel RealSense T265. We already have the undistorted images there. And of course there's also the TF frame IDs for the world or the odometry frame and the camera frame ID. So if you're using data not from the bag files, make sure that these are correct. Okay, let's actually run some of the data we've downloaded. So pop open a terminal, find where you put your bag files. So for us, it's in data IROS 2020. We just have the small ones here for the 600 megabyte zip file. So there's a couple of different bag files here, so you can use these to create anchors and query. They're all from the same scene. You can watch them. They're all a little bit different, and you can check out my stuffed animal collection. So what we're going to want to do is first start up a ROS core. Hopefully everyone is familiar with this level of ROS. If not, please go through the ROS tutorials. And then we'll want to actually launch our ASA ROS launch file. So ROS launch, ASA ROS, ASA ROS.launch. And in case you didn't copy and paste your account ID credentials into the launch file, you can just enter them here. So note the := And our account has the default domain, so we don't have to worry about this, but in case you don't, make sure you also enter the account domain there. So let's get started. Looks good. So here we get to see our account domain, the account ID, account key, and it successfully started running. And here you also see the parameters. So, okay, next up, let's actually run one of the bag files. So get back to the terminal where you have the bags. All you have to do is enter ROS bag play, bag 6 small, that's first one. And so this is running live. Let's take a look. So it says added first frame. And then we have no more output. So that's not really helpful to us, right? So we know that something was added, but not so good. So let's start again. And this time, let's also print the status so we get a little bit more output so we can debug this. And this bag file is only 17 seconds long. So let's run this again. And so here you already see a little bit of feedback. So it's saying there's not enough motion, which makes sense because we haven't put any data in yet. So let's play that back again. Okay, and now here you see live, there's you're getting user feedback. Maybe I'll make the term a little bit bigger, so it's either none or not enough motion. But you also get to see this ready for create progress and recommended for create progress. So once this hits 1, so ready for create progress, this means you have enough motion to create an anchor. Here we have twice as much motion as we need, which is good. So, and the bag file has finished running. So let's take a look at how we would actually use this data to create an anchor. So you can do this also from the command line, but just to show you with a nice GUI, we can do this with RQT. So pop open RQT. If yours looks different than that, go to Plugins, Services, and Service Caller. So if you refresh here, you get to see all the services that are available. So we don't have too many. We have Create Anchor, Find Anchor, Reset, and Reset Completely. And I'll walk through each of these. So first of all, we don't have any anchors yet, so we can create an anchor. So simply go here and call it. All of these are kind of optional. So what the parameter you can give is the anchor in world frame. So by default, the spatial anchor you're going to create is going to be aligned with a world or odometry frame. So, in the case of the Intel RealSense D265, this is just the place where it was when you started the drivers. In our case, I think it's reasonable to just do the default, but in case you want the anchor to be in a more physically meaningful location than the odometry frame, then you can just enter that here. So let's give it a call. So it's returned. So an important thing to note, it takes several seconds to create an anchor. So we can take a look at what's going on here. So it was successfully able to create an anchor, and I create an anchor with this ID. So if we're not looking at the output of the terminal, how do we figure out what ID was created? So so you can use ROS topic list, ROS topic echo, ASA ROS created anchor. So this topic is published after you've created an anchor. So here you see success true. Here's the anchor ID, and there's no failure reason because the status is okay. So great. So now we have an anchor ID. Very good. Next up, let's try to find this anchor in another coordinate frame. Next up, let's query this anchor. So we can, let's use the same account ID. We'll still, let's not print the status this time. I think that's not so useful when we're not creating anchors. And then what we can do is just pass in this anchor ID as a parameter. So again, we have it from the ROS topic here. And please note, after you create anchor IDs, if you don't write down the anchor ID, it's gone forever. So there's no way to retrieve it. So make sure that if you create an anchor, you write down the ID. Okay, great. So we can start running this. And you can see here, it's starting to look for the anchor. And so let's run one of the other bags. So let's run bag 7. If we go back here, okay, already, within 1 or 2 frames, it was able to find the anchor, and here you get the transformation to it. So in all of the bags I've recorded, it's actually the ground truth for this should be roughly identity, and that you see we're very, very close. We're just some centimeters off, and also the angular error is very small from identity, so that's quite good. And so how do we know what this transformation is without looking here? So we can again go to ROS topic echo, and here it's found anchor. Great, so we get to see within the camera odom frame, which is our world frame, the child frame ID is the anchor, and again you can change this by changing anchor frame ID here, and then here's the translation and rotation. Next up, we're going to look at how to track multiple anchors. So this time, let's start out not tracking any anchors, so just start a regular session. Then let's take a look at how you can track anchors by using a service call. So between takes, I've created a couple of anchors. I've written down their IDs here in a comma-separated list. So you can, anywhere there's an anchor ID requested, you can put in several. So in RQT, we're going to look at the find anchor service call. So here, again, this takes just an anchor ID, which is a string, but you can pass in a comma-separated list of anchor IDs, as you can see here. And so there's nothing being tracked yet. So let's then quickly start running one of the bags. So let's do bag 7. We can take a look at it in RViz. As you can see, nothing is happening. And then if we call the service, then all of the anchors kind of snap into place. And you can see I've placed them off the center. So this is done by just adding a transform when you call the create anchor tag. So here you can see all of the anchors that have been created. So another thing to note is that as I've pointed it out in the presentation, each of these anchors will only be kind of located once during a session. So this means that if your odometry drifts, then these might not be so accurate anymore. So next up, I'll show you how to start a new session. So this is done the same way as finding and creating anchors. So there's two service calls. There's reset and then there's reset completely. The only difference between these is reset will keep tracking the same anchors you were tracking before, so it'll keep querying the same ones, and reset completely will just clear this. So let's just do a reset of the session. And then let's run another bag and see what happens. So as you saw, the anchors snapped into place into more precise location, since the odometry frame changed a little bit from bag to bag. Now that you've learned how to use Azure Spatial Anchors with ROS, we'll now show you how to use mixed reality together with a real robot using Azure Spatial Anchors for co-localization. You'll need some kind of camera sensor and some kind of pose estimation sensor like the Intel T265 shown here. You'll also need to be on the same private network as the robot so you can freely access and communicate with it. Here we see Jackal Live, which is a sample launch file which you can find in the Mixed Reality Robot Interaction demo for how to run Azure Spatial Anchors live on board your Jackal. It's fairly straightforward. So the main things you have to add are, first of all, running the Intel T265 sensor. So here's the drivers for that. Then, of course, Azure Spatial Anchors. So here's a sample anchor ID we have put in here. Remember to also put in your account credentials. And here we're using an anchor frame ID of anchor. What this means is when this anchor ID is found, and please make sure to update this to be the actual anchor ID for your robot, it will be published on the anchor frame. Then we also have a new static transform publisher from anchor to anchor rod. This is necessary because of ROS to Unity coordinate frame conventions. Afterwards, what's actually consumed from the Unity side, as Eric will talk about in a second, is a transform stamped message. So we have a little script called tftransform.py which converts a single tf transform into a transform stamp message. So here we're resolving the transform from anchor rod, so again this Unity coordinate frame anchor, to the child frame, which is ODOM, which is what the Jackal is tracking its pose in. This setup, including with move base and ROS bridge and slam-g mapping, assures that you can send commands in the correct coordinate frame from Unity or from other mixed reality apps, and also receive correct path planning information. Next, Eric will talk about how to actually plumb this through on the Unity side.
If you want to use the Unity app with your real Jackal robot, there is nothing you have to change in the app. We'll still talk you through it, such that you know a few of the caveats you have to respect when working with Unity. If a real robot localizes against the spatial anchor, there is an additional transform we have to respect, which is the transform from the robot's spatial anchor to the origin of the ODOM frame where the robot lives in. In the Unity app, the parent anchor game object is aligned with the spatial anchor. The robot space location represents the origin of the ODOM frame. So the transform that the robot has from the spatial anchor to the ODOM frame is applied in the Unity app from the parent anchor to the robot space location. All objects in the robot space location now live within the ODOM frame. If you look at the ROS connector, there are two subscribers. One of them is the odometry subscriber, which subscribes to the odometry of the robot's base link, which is applied in local coordinates to the base link game object in the ODOM frame. Down here then is the stamped transform subscriber, which subscribes to the transform output, which is applied to the robot space location we just saw earlier. This basically is the transform from the spatial anchor to the ODOM frame. This is also published or applied in local coordinates. While Unity is using a left-hand coordinate system, basically everybody else is using right-handed coordinate systems. We have to account for that fact by converting incoming transforms correspondingly. This is handled by using the ROS to Unity method, which is an extension method from ROS#. Having said that, there is nothing else you have to worry about if you just want to use the app. But now you know what to think of if you want to extend the app to fit your own custom needs. We can also, of course, use the other control mode, which spawns this hand. If we now move the hand, the green robot will match its pose with the pose of our hand. If we move the hand far enough away, Jackal will try to match the end effector of the green robot with our hand. For that, the robot's base will move. As soon as the green hand is within the range of the blue hand, the end effectors will be matched.